podcast time.
So good morning, Dr. Ram. How are you doing?
Good afternoon, Michael. How are you?
Okay, so good period of the day, I guess. Today, I'm glad that you join us again, and I want to have a conversation on the, actually have a discussion and slightly deep into those details of the EPA's requirement for the OGI cameras, like the Appendix K. So go ahead, please.
Okay, EPA came out with this new regulation, and associated with this regulation is the requirement to do LDOR survey with OGI technology. This is for the first time OGI is the preferred technology for performing by the US regulator, performing the LDOR survey. So the OGI survey needs to be written into a methodology, and EPA published the Appendix K, which is the method for describing how to perform the OGI surveys, what kind of qualification the user need to have, and some requirement on the camera. So I will talk mostly about the requirement on the camera today. And the initial requirement is the camera must detect 19 grams per hour of methane in delta T temperature difference between the background and the air of 5 degrees from 1 meter distance with very low wind speeds. So a camera that pass these conditions can participate in this type of LDOR survey, but the lower or the higher sensitivity of the camera, if our camera in this condition can see 0.17 gram per hour, we have a much wider conditions, performance conditions that we can do the LDOR survey. And I will explain in a second with your leading question. Next question.
Absolutely. So, so the EPA set a standard for minimum detection level, right? But as you mentioned, it doesn't have any wind in that equation. So, if you go to any site in the world, most likely you will find days without winds, but there will be also days with a stronger winds and even harsh winds. So, how do you maneuver within this operation envelope, right? And how OPCAL is positioned here?
So actually, the EPA Appendix K set a requirement how to develop a performance envelope, and it depends on distance, delta T, temperature difference, and wind speed. You need to define what is the envelope that you can go out and do your LDAR survey with the OGI technology. And each manufacturer or vendor or even user needs to have this operating performance envelope before it goes out to the field. So we have developed in OPGAL the performance envelope. As I mentioned, since our sensitivity in these entrance conditions is so well below the levels are so well below the 19 gram per hour, we have the widest performance envelope in the market for performing this. So we actually can go up to, in some cases, up to 12 meter per second, which is
that's almost
25, 26 miles per hour, and we can still do the LDOR survey because we are so sensitive in these conditions set up by EPA.
Right. So basically, if you're talking about some, let's say, Houston, Texas conditions, that's one thing. But if you're talking for an offshore platform, you most likely will find higher winds. Like this way or another on the offshore platform in the open sea, that's what you will see. We'll see a lot of winds. Is it applicable there? I mean, is it still within, is compliant to this operation envelope?
I don't know what kind of LDOR survey they're doing in offshore, but if they do, it really depends on the day, and the temperature difference. As I said, it's not just the wind. If you have higher winds, you need to have higher temperature difference or get closer in order to have, you have a flexibility to play with these three parameters. You have the wind, you have the temperature difference, and you have the distance. You need to fall in this envelope of these conditions in order to do this survey. So if the highest wind, you need either to get closer or to make sure that you do your measurement with higher temperature difference. And by the way, after the Appendix K was published, we added a feature to our camera that we can measure the delta T, the temperature difference. So before we do the survey, we can examine different field of views and get a measurement of the temperature difference before we determine if there is a leak or we don't have a leak.
So I would say that from what you mentioned, there will be a triangle, right? So there's a wind speed, there's a delta T, and there is a distance.
Yeah.
So within triangle, would the ideal spot would be in the middle of that triangle, or should it be, or if I'm taking it from the middle to the edge of this triangle, like as I said, high winds, poor conditions. So what is the edge of this envelope?
So we have tables that on one side, the values are wind speeds. So if we have close range and higher delta T, we can allow ourselves much higher wind speeds. If we have a long distance and small delta T, we must have much lower wind speed. So it allows, so the value of wind speed that we can perform the survey really depends on the other two conditions, and we can play around within this triangle and make sure that we can detect we are within this envelope. If we are outside this envelope, we cannot do a survey.
So basically, it is up to the very experienced user to have the identification of the environmental factors, right?
Yeah, and we help them by adding this feature to measure it. He knows the wind speeds of the day. He knows the delta T. He knows the distance. He can figure out if he's within the envelope or he's outside the envelope.
That sounds very good. But is there any other features that might be helpful to be included inside an OGI camera that will keep you within this, within this regulation requirements?
I don't think it's very tough because you have this flexibility with this variable, and most OGI cooled cameras are well below this 19 gram per hour. Most of them can see below 1 gram per hour in laboratory conditions. So once you increase the distance, decrease the delta T, or increase the wind speed, you have a lot of room. So most days of the year in most sites you can go out. You need really harsh conditions in order not to be able to do the measurements. And you have everything to evaluate the conditions. You know the wind speed, you know the delta T of the scenery. And in days that the wind speed is very low, you don't even need to measure the delta T because you have flexibility. But in days of high wind speed, you need to pay attention more to the delta T and the distances.
Okay, I see. So the another question is, like, even though you will operate within this triangle or square envelope.
It's not square. It's an envelope. It's like a bubble.
Okay, so when you operate in how do you know that your equipment is sensitive? Like, how do you measure the equipment sensitivity to, let's say, methane?
Okay, so we added recently to our camera a feature that every time you perform a non-uniformity calibration on the camera, it also calibrates the sensitivity and check the sensitivity of the camera. So there is a term in thermal imaging, it's called noise equivalent delta T, temperature difference, NETT. But we converted it to noise equivalent CL, which is the concentration length of the noise level. And we determine what is the level to keep, and we check it every time, and we can check it several times over the day if the camera is performing. As long when we perform a NUC and it's below this threshold value, we are good to, the camera will see the gas in the sensitivity within the envelope. If we have something that is above or approaching the threshold and getting worse and worse, you should call us, and we need to maybe service the camera and see what's going on. Because usually for years, as long as the detector is in good temperature, the cool detector,
Yeah.
it should perform and keep up these values of sensitivity.
So and this is where I'm going. So you have the measure, or let's say you have the statement for sensitivity in a particular day, and you have this delta T feature, which you also can see the difference in the temperatures. So is there any log file then you can record those things, because that will eventually need to be added up to your reports, right?
So the calibration is automatically, every time you do a NUC, it will save the data into a log, and it will save the temperature and the values of the thresholds. And if something went wrong, you can see when it went wrong. Every time you turn on the camera, it automatically do this calibration. So you don't even if you don't do this NUC, every day when you open the camera, every time you open the camera, it will save a line in this log and keep all the information, so you can see when it started to go bad, and how fast it went bad, and so you have the whole history of the calibration
So
values.
the other thing is that we mentioned delta T reflection on that screen and on that report. So how do you really know that you're in delta? I mean, how do you grab the initial temperature, or where in what part of the day you grab the initial
No,
temperature measuring? How it's done?
you can make sure that the lid of the camera is in the shade, and you can put it on, and once we have a feature that you can sample the earth temperature. You actually
Right.
take the lid temperature representing the earth temperature, and you measure it with the camera. We found out that a better way to do it is to take a white sheet paper, and put it in front, wave it in the air for several times. Don't take it out of your pocket, because once you take it out of the pocket, it will have your body temperature,
Right.
not the air temperature. You put it in front of the lens, you sample the air temperature, and that's how we know the delta T, the air temperature. And you get in the center pixel, group of pixels in the camera, you get the reading of the temperature difference, and you can scan the scene and see what is the average
So that will be the reference, right? And then everything that we'll look upon, and that's what you're saying, it will reflect the difference from that reference temperature, correct?
The air temperature, you mean?
Right. Like if you grab this with this piece of paper, you grab that temperature measurement, and then everything you will be looking at. And if
Yeah. But you need to do, if you do it in the morning, I would do it every time you feel like, if you're in the morning and the temperature going up, do it occasionally. Do it every half an hour. It's taking you a few seconds. You just need to go there, press the bar, put the sheet of paper, and it's few seconds, and you have an updated air temperature, which is important for the delta. Every time you need to do a delta T measurement, it's not all the time. You can look for your leaks, but when you get to a scene that is important, you have high winds and it's a long distance and you're not sure you're inside the envelope, that's when you need to take a measurement of the delta T. Only before you take the measurement of the delta T, it's wise to take a measurement of the air temperature by putting the lid or a sheet of paper.
So having all those features built in, and we have this quantification sequence that we could run or could not run, depending on whenever we're doing detection or quantification. Like for me, it's very important to understand like when you do decide to do the quantification, how would the report look like? How will it all be transmitted on my report spreadsheet? All of this data we collected. So we're talking about the delta T, the distances, the materials, the compound, the wind speed, etc., etc., etc. Will it be on my report? So each and every quantification will include that, or it will be overall for the whole day?
Okay, before you do quantification, you cannot do quantification on the fly. It's not automated. You need to put it on a tripod, and you have a menu. Inside the camera, you need to put the distance. It's very important because the pixel size, I mentioned the wind speed and all of it really depends. The calculation of the wind speed and the size of the plume in meters or in yards, it depends on the distance from the source. So we really need to put the distance, the lens, all the type of gas, the compound. We put all the information in the beginning, and then we start recording the quantification for 1 minute or 2 minutes. And in the end, you'll get all the values average, and you get one number of the quantification with everything, the air temperature, all the values that you put in this menu will be in your report. So it will be reported as one Excel sheet.
So the same can apply to a long range quantification. I mean, that's how it really will look like. I mean, if I'm increasing the distances, will the calculation self-correct itself? Or for instance, just another example that I have, or another question that I have, what will happen if I'm doing it on a clear blue sky background, and then there will be some clouds coming crossing that plume sector? What will happen?
What will happen at the time that the clouds come in? It stops the quantification, and when it's clear, it will resume the quantification. It can detect the cloud and it stop it. We added a feature, actually, the numbers will stop showing up on the screen. And if you want to stop the quantification and start it after a time, you can do that. If you have only clouds and it's very stable, like overcast skies, you can stay. And all we need to know, it doesn't change. Once you have clear sky and a cloud comes in, it will change.
That's a dramatic change.
A dramatic change. So the quantification will stop, will not include awkward value into your average.
Okay,
and it will be resumed after the cloud is over, and you can have one file only on clear sky. And actually it can resume if it's changing. If the cloud stay for a long time, it can resume when you have like static condition for 10 seconds. It will resume calculation on the cloud.
So this is my next question. What happens if it's like breaking cloud? So you have a partially clouds entering.
It doesn't matter. We know how to handle if the temperature of the background is changing on the scenery. We know to update, but in the transition area, we just cut out this information and do not include it in the average. Okay. So we filter out the data, the transition between clear sky to the cloud. If we have constant cloud for the rest of the time, we can collect data. After 10 seconds, it will resume calculation, and it should be the same. And now about long range, you ask on that question. Yeah. This is up to a couple of 100 meters. It's doesn't matter. One of the features in the quantification that we can replace the lens from 30 millimeter focal length to 75, and it's magnified by 2.5 factor, and we can quantify. And actually what we found, the usability of quantification of OGI is mainly on this long range vents on the sky background, because this is almost the only way to quantify these sources. And these sources are very significant, because close to the ground sources, pipe is leaking. There are other methods that can be more accurate than the OGI. And even these methods use OGI to see plume capture. You need OGI also for these methods. It's like called high flow samplers. It's like a vacuum cleaner that suck all the emissions into a detector inside this vacuum cleaner, and you can get the flow rate very accurately. OGI accuracy cannot compete with this, but how you get this vacuum cleaner to 70 meter
you cannot
stack? So inaccessible sources, remote sources, that's where our technology is the best, and it was proven in a blind test in Europe. We actually source level measurement quantification, we perform the best.
Right. So I was thinking also, like, you cannot fly there, you cannot get up there, you cannot use. So the only actual source or actual equipment you can use is an OGI with a telephoto lens that will allow you to get there optically, right? Yeah. And then to measure it.
Yeah. Up to 50 meter, I don't even consider to replace the lens. Only
Yeah.
you know,
And they normally they count it like in Europe. They say that all of those big vents are considerably the highest emission source on the plant itself. So covering those, that might lead you to 70% of coverage for the whole site, right?
yeah, even more.
Even more.
Even
Oh,
more.
okay.
With our experience, sometimes it's 90%.
Great, great. Okay, so ladies and gentlemen, I guess this session is coming up to its end. Thank you very much, Dr. Ram.
Thank you, Michael.
See you next one.
Bye.
Ciao.